This time we're going to talk about the inverse function. The first thing we need to talk about is a special kind of function called a one-to-one function. And it's pretty easy to understand what a one-to-one function is. If you notice in this first example here, 1 goes to 5. The number paired with 2 is 6, and the number paired with 9 is 3. Now obviously, each x has to have exactly one y because it wouldn't be a function if it didn't. But in this case, notice straight across, each y has one x. Over here, suppose 1 goes to 5, and 2 also goes to 5, and then 3 goes to 6. Now it is still a function because each x has exactly one y. 1 has exactly one number paired with it, and that's 5. 2 has exactly one number paired with it, and that's 5. 3 has exactly one number paired with it, and that's 6. But in this case, 5 has two different x's paired with it. So this is not a one-to-one. In math language, it's referred to as a many-to-one, as opposed to a one-to-one, like this example here. The important thing about one-to-one functions is a one-to-one function will have an inverse that is a function. So that's why we study one-to-ones in order to learn about inverse functions. In order to test to see if a function is one-to-one, if you're given ordered pairs, you can look for this situation here. If you're given the graph of a function and you're trying to determine whether it's one-to-one, the horizontal line test is the way to determine it. Basically, the horizontal line test says if I can draw any horizontal line and hit the curve at more than one point, then it's not one-to-one. In this case, any horizontal line that I draw, using the pen as an example here, will only hit this curve at one point. So this one is one-to-one. I'll try to write it in here. However, over here, there is a horizontal line that would hit the curve at two different points. Yes, there are some down here that don't, but if one hits it at more than one point, then it is not one-to-one. So in this case, it's not one-to-one. Okay, so the horizontal line test is to determine whether a function is one-to-one. Now we're ready to talk about the inverse function. And basically what the inverse function does, the inverse of f, written as f to the negative 1 power. I know we normally think of negative 1 power meaning reciprocal, but in this case it means inverse, not 1 over. The inverse of f, written f to the negative 1 power, undoes f. Now what does that mean? Well, here's what it means. If f takes 3 and goes to 5, in other words, if f of 3 is 5, then the inverse of f would undo this. It would take the 5 back to the 3. So basically, what the inverse function is going to do is it's going to turn around all the ordered pairs. Instead of 3 going to 5, 5 is going to 3. So basically what it's going to do is the domain is going to become the range, and the range is going to become the domain. And that's the premise that we're going to use for finding the inverse. So, now let's talk about how to find the inverse of f. So I'll move my paper up here. Now there are three situations. If you are given ordered pairs, if f is written in a list of ordered pairs, then basically you turn the ordered pairs around. That's simple. Just turn the ordered pairs around like we did up here. 3 goes to, this would be 3, 5, and this would be 5, 3. So, as an example, if f creates this ordered pair, 3, 5, 7, 9, -2, -4, and 8, -16, then the inverse of f would turn these ordered pairs around. So f inverse, you would get 5 comma 3, make my pen right here, 9 comma 7, negative 4 comma negative 2, and negative 16 comma 8. So basically it's just going to turn these ordered pairs around. And that's basically what we're going to do in the other methods. If you're given the function in graph form, then the way that you're going to achieve this up here is you're going to take all those points. Now basically if you're starting with a graph, your F inverse is going to be a graph. So what you're going to do is you're going to reflect all the points of the graph over the line y equals x. The line y equals x would be a line at a 45-degree angle, and all the points over here would just go straight over there. All the points on the graph that were here would go straight over there. And there are some examples in the book on that. I'm going to go to the next example to show you the algebraic way of getting the inverse. And that is the third one. I'll move this up. If the function is given in equation, technically we're supposed to say rule form. If it's given in equation form, then the technique is as follows. I have an example here that we will apply the technique on. Example 2, find F inverse if f of x equals 2x plus 5. Notice we're not given any ordered pairs to turn around. We're not given the graph. We're given the rule that will generate the ordered pairs. So since there are so many ordered pairs, it would take too long to turn all the ordered pairs around. And besides, I'd like to know how to generate ordered pairs according to the new rule for this. Now notice, it's going to be a rule, an equation, but it will be different from this one, because this new one is going to generate the ordered pairs that this one generates in reverse. So here's the procedure, the technique that we're going to use. The first thing we're going to do is we're going to interchange the x and y in the equation that you're given. That's the first step. The second step is to solve for the new y. Now once you've solved for the new y, you're going to replace that y with f inverse of x. The reason we do this is because if you start off with y equals this and you wind up with a new equation y equals, we like to differentiate between the two equations so we'll know which one to use. So we name it f inverse of x. So now we'll do this example using this technique. Alright. Notice I put y in place of f of x. Y equals 2x plus 5. Now, step 1 says to interchange the x and y in the equation, so I'm going to do that. So in place of y, I put x. Where x was, I'm going to put y. So I have x equals 2y plus 5. Step 2 says solve for the new y. So basically, I'm going to get this y by itself, which means I've got to move the 2 and the 5. And the way to do that in the correct order, of course, is I'm going to subtract the 5 from both sides. So I have x minus 5 equals 2y. And if you don't mind, I'm going to turn this around. And I'm going to divide both sides by 2 in order to get the y by itself. So I have y equals x minus 5 over 2. Now, notice that this y here is according to the inverse. This is going to generate ordered pairs in reverse of that one. And we'll verify that in just a moment. So now the last step is to replace this new y with f inverse of x. So that's what I'm going to do. In place of y, I'll write f inverse of x equals x minus 5 over 2. Now, what I'm going to do is just verify this. So here's what we're going to do. Let's just create an ordered pair in the original function. So let's say x is 1. F of 1 means put 1 in here and work it out. 2 times 1 is 2, plus 5 is 7. So what we just did was create the ordered pair 1, 7. Now let's look at F inverse, and remember what it's supposed to do is turn the ordered pairs around. So I'm going to look at F inverse of 7. So I'm going to plug 7 in here in my new formula for F inverse. 7 minus 5 is 2, and 2 divided by 2 is 1. So what F inverse created was the ordered pair 7, 1. So it's doing what it was supposed to do, creating the ordered pairs that this one creates, but in reverse. Now it's your turn. Find F inverse if f of x equals x minus 3 over 2. And I'll put the answer down here for you. You can stop this and work it out and then look at the answer. And now you can verify that this will create the ordered pairs in reverse that this one creates.